Hello, my name is Sanjay Pirnat, and today I'm going to present our paper towards sustainable deep learning for wireless fingerprinting localization. We'll start with a quick introduction, then go over the challenges that we have set for ourselves and present the contributions that we made. Then we go over the architecture and the computational complexity of it. And after we get the performance of the model, we'll finish with the conclusion. Location-based services provide location as a service. They're already popular with end users and will be in use even more in the future. The most popular is Global Positioning System, widely known as GPS. It integrates data from satellite navigation systems and cell towers and is used daily in navigation systems. Deep learning can also be used for localization. It performs very well, and it's therefore a promising technology to be used for location-based services. But in it lies a problem. Deep learning is quite power hungry. And since it's estimated that there will be 7.4 billion mobile users by 2025, which would result with at least 65 tera predictions each year, with such a large number of predictions, we should also focus on making things energy efficient. Because unfortunately, electricity has to be produced somehow, and that always includes CO2 and gases equivalent to it as a byproduct. Our objective was to solve the problem with deep learning as simply as possible with a software solution. We wanted to make a deep learning model that was on parallel in performance with the state-of-the-art models, but with much less power consumption and therefore with a much smaller carbon footprint. In our paper, we therefore propose a new deep learning model for indoor localization and prove that its performance is comparable to state-of-the-art models while being much more energy efficient. Our contributions are as follows. A new model with a kernel and max pool that extract the most useful information from the subcarrier of a single antenna at a time. We elaborate on a methodology for computing computational complexity during training and operation of a deep learning architecture. In a carbon footprint study, we showed that the proposed deep learning model during training produces only 58% of the carbon footprint and maintains 98.7% of the overall performance. The localization was done using a multiple input, multiple output antenna array to learn the location of the targeted antenna. The way it works is we start with an antenna array which has dimensions m by n. We used a data set from a competition CTV 2019. The data set was recorded on 16 antennas from an antenna array, and it contains 924 samples from each of them. And each sample is a complex number which has real and imaginary part. Then the antennas in this array pick up the disturbances in electromagnetic waves caused by the targeted antenna that we want to know the location of. These disturbances differentiate based on where the targeted antenna is located, and it is actually possible to train a model to locate the targeted antenna using those anomalies. To train the model, we also need GPS to test it, but such GPS data is of course not needed when the model makes predictions later on. The data set from the antennas comes in a shape of 16 by 924 by 2. In given situation, it's the best if we shape filters of convolutional layers and pooling layers into the shape of 1 by n. Such filters and max pools move over the subcarriers of a single antenna at a time and produce better results. Used ResNet 18 as an inspiration for our model because it's the least complex ResNet deep learning model, and it's very adaptable to less complex images constructed from time series. We changed the kernels and stride of the convolutional layer to better suit the situation, like we explained before. Then after those layers, we continued with ResNet blocks in which we decreased the number of filters by half. And after that, we used the ReLU activation function with the parameter alpha set to 10 to power of -3 instead of regular ReLU. And for the output, we added another layer with 3 nodes, which give X, Y, and Z coordinates of the location. Next, we want to calculate the energy consumption of the model so that we can calculate the carbon footprint. We have to calculate the flops, which are floating point operations, of all layers that add significant complexity to the architecture. Here we started with a fully connected layer, also known as a dense layer. Complexity of the dense layer depends on the input and output size. If we multiply input and output, we get the amount of MAC operations that the layer has by itself without the activation function. MAC operation is a multiply accumulate operation, and therefore each MAC operation consists of multiplying and accumulating. Hence, each MAC operation equals to 2 flops, so 2 floating point operations. To get the real amount of flops, we also have to take our activation function into consideration. In the example of the dense layer, that results in having to add the output size to the equation if you're using ReLU activation function. Next, we have convolutional layers, which in most cases add the most complexity to the model. Flops per each filter of the layer depend on the dimensions of the filter, dimensions of the input tensor, stride dimensions, and padding dimensions. We wrote the equation in the way that it is inclusive for different shapes of filters and input tensors. So we have calculations for rows and columns separated and multiplied with each other. The first part gives the height, and the second part gives the width of the output tensor. And then the last third part provides the number of computations per filter for each of the channels, which are marked with C in the equation. Each of the 3 parts, we have to add 1 for the bias, and then to calculate the total amount of floating point operations in a whole convolutional layer, we have to account for the number of filters which are in the convolutional layer, and we also have to account for ReLU activation function. So we take flops per filter and add to them the number of computations per filter for all of the channels, and then we multiply both by the number of filters. And then the last type of layer that we're going to calculate the flops for is a pooling layer. We calculate flops for a pooling layer a bit like we calculated flops for each filter of the convolutional layer, since it's like one filter from it. And now that we're able to calculate flops of the model, we can start with calculating energy consumption. We do that by calculating the energy used in forward propagation, which enables us with calculating energy for training or prediction making. It depends on the sum of all flops from the architecture, and then we divide that with the GPU performance, which tells us how many flops per watt the GPU can handle, and then we multiply it all by the number of samples and the number of epochs. This is theoretical energy consumption, since it's calculated from flops to watt, which is a data given by NVIDIA or some other GPU producer. We can approximate that the back propagation requires twice as much energy as forward propagation. Energy used in training consists of energy used in forward and back propagation. And with the previous approximation, this equals to 3 times the energy used for forward propagation. Energy used to make a prediction is equal to energy used in one forward propagation, except the number of epochs is of course 1 in this example, and that's why we don't write it in the equation. And finally, after this intense math session, we can calculate the carbon footprint. Carbon footprint of the model that we want to calculate depends on the carbon footprint of the power plant and the energy used in training or prediction making. To calculate it, we simply have to check how many grams of CO2 equivalent is being produced with each kilowatt hour of electricity on which the GPUs are running. In our case, we use Google Colaboratory, which most likely has its GPUs somewhere in California. And California produces around 250 grams of CO2 equivalent with each kilowatt hour, according to electricitymap.org, that is. We multiply that number with the energy used in training or prediction making. We'll have to be careful because the aforementioned equations with which we calculated the energy give the result in joules. So we have to remember to convert them into kilowatt hours, and then we'll end up with grams of CO2 equivalent produced by the deep learning model like we want to. To compare our models with the others, we tested them in 4 different categories. Samples used for training are marked with black color in the pictures, and samples used for testing with red color. The first category is random. In this category, we tested the model on randomly selected samples across the area of measurement. The second category is narrow edge. Here we tested the model on the narrow edge of the area and trained everywhere else. Then third category is wide edge. Here we tested on the wide edge of the area, trained everywhere else. And then the last fourth category is within. Here we tested on a circular area within the area of measurement and trained everywhere around the circle. Here are some results that are also in the paper. We compare our model with the other 2 that were among the best, free and comparable in performance with our model. They have the best 3 have results written in bold. We measured accuracy with root mean square error and with mean distance error. If we focus on the best 3, we can see that our model performs comparably as well. So we were happy with the results because our model reached 98.7% of accuracy of the best model overall. And here are the results that we got for training the top 3 models according to our equations for carbon footprint. Our model did well. It used a bit more than half of the energy used by the second most efficient model, and therefore produced only a bit more than half of the carbon footprint of the carbon footprint. We got these results by feeding 32-bit floats into every model. And here we have the results for making predictions with the models. The graph is in a logarithmic scale because it's easier to read this way since the differences between the models are quite large. So in conclusion, in this paper, we proposed a new deep learning architecture used in PeerNet Echo model for indoor positioning, paying special attention to energy efficiency during training and operation with only minor performance degradation compared to similar models. In developing the architecture, we started from the ResNet 18 architecture, and firstly, we reduced the size of the filters, and then secondly, we adapted the pools while being aware of the specificities of the data available for the problem. Since there is a paucity of work evaluating the energy efficiency and computational complexity of deep learning models, we also elaborated the methodology to benchmark the 3 best performing models in terms of their carbon footprint for training and prediction making. We have shown that it is possible to develop deep learning models for wireless fingerprinting localization that optimize both accuracy and environmental cost, providing a viable alternative to models that focus only on accuracy. So that will be all. Thank you for listening to our presentation. I'll be happy to take any questions you might have.